let me begin as background by talking about some classical number theory. In particular, I want to start with Dirichlet's theorem. So, in the field of number theory. And please let me know at any point if anything I say is unclear, or if you have any questions. So the Dirichlet's theorems says that for, let's say n, a natural number, and a an integer, there exist infinitely many prime numbers which are congruent to a modulo n, as long as the a and n are relatively prime. So their GCD is 1. They have no common factors. Under that condition, they have infinitely many prime factors. And to orient you, I'll point out that this condition is clearly a necessary condition. In other words, the converse of this theorem is easy to prove. So the only if direction, since if they had some common factor, if d divides a and d divides n, that would imply d divides p. And so because a prime has no factors other than 1 in itself, that would imply that d is equal to p. And so there could only be one such prime. So for there's infinitely many if a is relatively prime to n, and there's only one at most if they share a common factor.
So if capital N is 0 and small a is 1, then I think well, it's an exception to this. Number is
yes, n should be, well, I think natural numbers will be positive for this talk. Yes, right, I should always, okay. Maybe one should never say natural numbers because it's confusing. N is a positive integer. This is not a very precise statement. Just to say that there's infinitely many, it would be more useful to know like when in the number line you see some of these primes. So one wants to know not just how many there are in the whole number line, but how many there are in a particular interval. So a more precise theorem is the prime number theorem in arithmetic progressions, which states that the number of primes in the positive integers such that p is congruent to a modulo n and p is less than x, this is equal to, so one over phi of n dy over log y plus O of, depending on q, of x e to the minus c root log x for some c. Okay, so let me explain what I've written. So I'm going to, this is, I guess x is here is a positive real number, maybe greater than 2 just to be safe. X is a real number. And we're counting primes congruent to a mod n less than x. And we have a formula for them. And the formula is expressed in terms of this logarithmic integral. So this is a little bit more precise version of the prime number theorem than saying the number of primes up to x is x over log x. A more accurate estimate is this integral, dy over log y, integrating from 2 up to x. And so that's the total number of primes. And what we're saying is the primes are equally divided into all the possible congruence classes mod n. The number of congruence classes that are possible, so phi of n, write it up here, then is like the number of residue classes modulo n that are relatively prime to n. So then this is a big O notation. So that this is the main term, and the error term I'm saying is bounded by a constant times x times e to the minus c root log x, and my constant might depend on q. Oh, sorry. Yeah, sorry. Oh, sub n. Sorry about that. Just try. Yeah, it should be more. And C doesn't, but C doesn't depend on n. C can be made explicit. And this is not, in fact, the optimal statement of the theorem. This is even slightly simplified because you could really give an explicit dependence on n here if you're careful, although a kind of bad one because of the problem of C equals zeros.
Can you say the power of x maybe? Like some, like x e to the minus, can you get x to the fifth, 5 divided by 6 or something like that?
That's a good question. Let me answer that shortly. The short answer is no, but I'll give a longer answer in a moment. Yeah, so this is a powerful result because it gives you a reasonably precise, although not as precise as you could hope for, a reasonably precise answer for the number of primes in progressions up to a given point in the number line. So these are two classical results in analytic number theory. And the proofs of them both rely on the same idea, which is the idea of studying the Dirichlet-L function. A function chi from the positive integers, let's say, the complex numbers, is a Dirichlet character mod n if 1, we have chi of nm equals chi of n chi of m for all nm. 2, chi of n plus capital N is equal to chi of n. We call that maybe a little chi of d plus n is equal to chi of d for all d. And 3 is that chi of d equals 0 if and only if GCD of d of n is 1. So yes. So anytime you're working with numbers, the hard part is sort of going back and forth between addition and multiplication. And so Dirichlet characters do that very elegantly. Their first property is multiplicativity, showing they're compatible with multiplication of natural numbers. And the second property is periodicity, that they're periodic with period n makes them very compatible with addition of natural numbers. And then the third property is some kind of normalization. when we have such a Dirichlet character, we define the Dirichlet L function by Ls chi is equal to the sum from n equals 1 to infinity chi of n times n to the minus s. So it's a variant of the definition of the Riemann zeta function, which incorporates this Dirichlet character, which means it incorporates congruence modulo n. And just like the Riemann zeta function is very helpful for counting the prime numbers, these Dirichlet L functions are very helpful for counting primes in arithmetic progressions. I guess one way to see that is using the Euler product. We can describe it equally well as a product over prime numbers of 1 over 1 minus chi of p to the minus s. And by basically taking logarithms of this formula, you can see that if you understand the Dirichlet L function, you can understand primes in progressions. So well, one Dirichlet character is special. We have the trivial character, which is defined to be 1 if d is relatively prime with n, and 0 otherwise. And then the key property is that if chi is not chi 0, then Ls chi is an entire function. It is holomorphic on the whole complex plane. And then it's not so hard to show using the Euler product that Ls chi is non-vanishing if the real part of S is greater than 1. And the way we obtain results on primes and arithmetic progressions, the primary thing we need to do is to improve this non-vanishing. So Dirichlet, for his theorem, essentially only needed to show that L1 chi is not equal to 0, and that implies Dirichlet's theorem. And then you can furthermore show that L of 1 plus it chi is not 0 for t and r. So there's a vertical line in the complex plane where it doesn't vanish. And then using a neighborhood, also non-vanishing near that line. And that implies the prime number theorem in arithmetic progressions. And if we could make further progress on the non-vanishing of this function, that would imply further results on primes in progressions. In particular, if Ls chi is non-zero, for all chi mod n. And all the s with the real part of s greater than alpha, then we get the set of P where P is congruent to A mod n and P less than X would have size 1 over phi of n, integral from 2 to x dy over log y, plus O of x to the alpha plus epsilon. This is for all epsilon greater than 0. So if you want to get a power savings, you want to get an estimate of size x to the 5/6 here, for example, all you need to do is show non-vanishing of this L function at all points with the real part greater than 5/6, which is probably very, very hard to do. And in particular, one special case, the case of alpha equals 1/2, so the case where there's no zeros with real part greater than 1/2 is called the generalized Riemann hypothesis. So showing non-vanishing of this function out to the line 1/2 would be 1/2 plus IT is one of the most important problems in number theory. It's a generalization of the Riemann hypothesis, and it would imply a very strong estimate for the number of primes in progressions. Actually, let me say something about the significance of this estimate. Why is x to the 1/2 plus epsilon the right estimate to look for? Why is that the strongest estimate we can believe? Why couldn't we choose alpha less than 1/2? So one reason is because of the functional equation of the zeta function. Using the functional equation, you can see there must exist zeros with real part alpha equals 1/2. So, and you can calculate and find such zeros, so you know the error term can't be greater than, it can't be less than x to the 1/2. But there's also a conceptual reason, which is that if we think of the primes as being kind of random, as a random set of numbers where each positive integer has a small probability of being prime. For instance, to make this work, you could say that each positive integer n has a 1 over log n probability of being prime, and the expected number of primes would be very close to this integral. If you have a random set of numbers like that, then the error in your prediction for how large the set is, the difference between the size of the set and its expected size, will always, by a central limit theorem, be roughly proportional to the square root of the expected size of the set. So you really would expect, if the primes are random, to have an error of size x to the 1/2 here. Or I guess for primes and progressions, if n is large, I should say it's x over n to the 1/2. So there's kind of an expected error from the random model is like maybe O epsilon of x over n to the 1/2 plus epsilon. So this is kind of the best error we could hope for, because it's very hard to believe that the primes are better distributed than a random set of numbers. And so for n small, this is the same as what you get for the generalized Riemann hypothesis. The generalized Riemann hypothesis is the strongest estimate you can hope for. But for n large, you could maybe hope for an estimate that's a little bit better than you get from GRH. You can hope for additional savings in terms of n. Because the expected size of this set is only of size roughly x over n. Because, yeah, we're dividing by phi of n, and phi of n is roughly the size of n. So the generalized Riemann hypothesis is a very hard problem about these L functions. But it's not the only problem. There's a lot of other interesting questions about the behavior of these complex analytic functions. So another kind of interesting question we can look at is a question that's kind of statistical. So these are questions where we ask not what is the value of this function at a particular point, but what is a typical value if you look at many different points. For example, many different points on the critical line 1/2 plus it. How does the value of the function vary? How large is it typically? Or at the same point, for many different chi, how does this function behave as chi varies? What happens on average over chi? And there are many kind of fruitful questions about the L functions that have this statistical nature. So the main example I'm going to think of about today is the question of moments. And these would be sums over characters chi. Maybe we take all chi mod n of the L function at some point. Usually the point 1/2 is the point we're interested in the most because it's at the center of everything. Raised to some power. And then the complex conjugate of chi raised to some power. So how can we give an approximate value for these sums over chi? If we could do that for many values of a and b, it would tell us a lot about how the value L 1/2 chi is distributed as a random variable for a random chi, which is another question. Question number 3. But it's very, very hard. So it is known, if we're summing over all chi mod n, this is known for a at most 2 and b at most 2. And then maybe a equals 3, b equals 0, 1, something like that. So it's only known for a few values of a and b.
Conjugating the L function or the character?
I'm conjugating the value because I'm taking the point 1/2. That's equal to what I get by conjugating the character. And so in particular, if a is b, since I'm multiplying by its conjugate, I'm taking the absolute value and raising to a power. So we're kind of only considering the size and not the argument. But I'm also considering the case where a is not b. Yeah, and then yeah, you can think of it as the conjugate character, but I just mean the conjugate of the value.
Can you have 0 at 1/2?
So I think it is conjecturally no, but I think it's unknown. Yeah, or no, is there a congruence? Unless there's a congruence obstruction yeah, no, I'm pretty sure it's unknown. But conjecturally, you shouldn't get 0 at 1/2. But the best thing we can do is give estimates for how often it's non-vanishing at 1/2, like how many characters is non-zero. And you can get estimates for how many characters is non-zero exactly by considering these moments. Okay. See if I can raise that one up. Oh, doesn't go that far. Oh. All right. So both these questions about L functions that I mentioned, both the generalization and hypothesis and the moments are very hard. And so what I want to do is talk about an analogous question in a different setting. So it's often a very productive thing to do when you have a hard problem is to consider a similar problem somewhere else. And so the setting I'm going to work with is a setting of polynomials in one variable over a finite field. So I'm going to choose FQ, a field with Q elements. And so for almost everything I'm going to say in all my lectures, it's sufficient to consider the case where Q is prime. And so FQ will just be the integers modulo Q. But we can also consider prime powers with no loss. And so by FQ adjoin T, I mean the polynomials in one variable. So I just mean expressions like t to the 7 plus 2t plus 1 would be an element of FQ adjoin T. Right over here. And I think about FQ adjoin T as being very analogous to the ring of integers. So these two rings have a lot of algebraic properties in common. We can add and multiply by similar algorithms. The only difference is for polynomials, we don't have to carry when we add or multiply. For integers, we do. We can divide by polynomial long division, which is the same algorithm as integer long division. And so using that, we can do Euclid's algorithm for polynomials. And that lets us see that the ring has the same algebraic properties in terms of unique factorization into prime polynomials as the integers with unique factorization into prime integers. And kind of the similarities continue on from there. So using a plus, I'll denote the set of monic polynomials. Which is in other words, with leading coefficient 1. And I'll think of the monic polynomials as being analogous to the positive integers. So every integer that's not 0, you can write uniquely as a positive integer times plus or minus 1. And every polynomial that's not 0, you can write uniquely as a monic polynomial times a non-zero element of this finite field. So the so for questions where we care about positive integers, we'll use the monic polynomials. And I have a notion of the absolute value of a polynomial, which is the same thing as just the size of the finite field q raised to the power of q to the degree f, or raised to the power of degree f, which we can equivalently write absolute value of f is the cardinality of the quotient ring of fq joined t by f times fqt. And so this is analogous to, well, the absolute value of a number, which is also the cardinality of the quotient ring integers modulo nz. And so what am I going to be doing in this series of lectures? I am going to be taking advantage of this analogy in different settings to either mostly take classical problems in number theory, occasionally take theorems in number theory, and to use this list of analogies, which will gradually get longer and longer, to transform them into problems in the new setting. And so one reason to do this is because when we transform them into the new setting, we get easier problems. We can make progress on them when we couldn't before. But I want to kind of focus on a slightly different reason, which is that when we transform them into the setting, we see new connections with other fields of mathematics. So I want to explain how connections to especially the fields of algebraic geometry and topology, but also to other fields like probability, appear when we kind of use this analogy. And what I'm going to do today is give the first example of that and kind of set the template. And I'll do it using this notion of L functions and this problem of moments of L functions. So let's give first the definition of a Dirichlet character. So I'm going to have a function that's now evaluated on polynomials over a finite field, but it's still valued in the complex numbers. I don't want to change the place where the values of my arithmetic functions live. Just the source, not the target. Is a Dirichlet character mod G. So first, chi of f times h is equal to chi of f chi of h for all f, h, and fq join t plus. So that's the analog of multiplicativity. The analog of periodicity becomes slightly more complicated. Chi of f plus g times h is equal to chi of f for all f, h, in fqt plus. And then third, chi of f is non-zero if and only if GCD fg is 1.
But you don't know if f plus gh is monic.
Correct. So yeah, so I checked that if you, okay, so you only consider the condition in the monic case. and that gives you something. And you could also extend the function to non-monic polynomials and check the condition in that setting, and this gives you the same thing, so it doesn't matter. Yeah, I mean, I could say, I could say the degree of h is greater than degree of f minus degree of g if you want, and this would be sufficient. And then, with the definition of a Dirichlet character, we define the Dirichlet L function the same way. Ls chi is equal to the sum over f monic polynomials, chi of f, absolute value of f to the minus s. Here's put this absolute value in to make it a real number. And so now that we define the Dirichlet L function in the setting, we can study their properties. I want to send that one up. Oh, I even have another one back there. OK, let me bring this one back down and erase it. Let me not try to manipulate 4 at once. So we can see what Ls chi is doing a little bit more clearly if we expand the definition out, expand out the definition of absolute value of s. So we can equivalently write Ls chi, the sum over monic polynomials, chi of f, times q to the degree f raised to the power minus s, which is the same thing as q to the minus s degree f. So each term in the sum ends up being a monomial in q to the minus s. And so we end up with a power series in q to the minus s. Ls chi ends up being in this setting, again entire, for chi non-trivial. But for a more elementary reason, because it is a polynomial in q to the minus s. Yes?
I don't understand why the degrees on the power, on the exponent.
So it's because I defined the absolute value of f as q raised to the degree f. Yeah, so q to the degree f to the minus s is the same thing as q to the minus s to the degree f. So why is it a polynomial in q to the minus s? Well, you can expand, you can take this sum and separate out the terms only of a given degree. So let's sum from d is equal to 0 to infinity. Now the sum of f and fq joined t plus. Degree f is d. Chi of f this inner sum then gets multiplied by q to the minus d times s. So this is an equivalent formulation. And this sum, I claim, vanishes for d greater than or equals to the degree of g. Because each residue class mod g occurs the same number of times, q to the d minus dig g times. And the sum over residue classes vanishes. The sum over residue classes vanishes by orthogonality of characters. So that implies that this power series, all the coefficients past the degree of g will vanish, so you get a polynomial in q to the minus s of degree at most the degree of g minus 1, which in particular is going to be holomorphic on the whole complex plane. And we have other properties that are kind of analogous. So we have the Euler product, Ls chi. Using unique factorization, we can see it's the product. So the analog of a prime number for me is a prime polynomial, which is an irreducible monic polynomial. It's a polynomial that can't be factored into monic polynomial factors other than 1 in itself. We have 1 over 1 minus chi of pi, q to the minus s degree pi. And this Euler product does for us the same two things it does over the integers. On the one hand, this implies that Ls chi is not 0 if the real part of s is greater than 1. And then it also implies if we can improve the non-vanishing, we get information on like the analog of the primes in arithmetic progressions problem, which would be the set of pi in fq adjoint t plus, such that pi is congruent to a modulo g, and pi is irreducible. So this is like, I need degree of pi is equal to some fixed n. So monic and irreducible is the analog of prime. This congruence condition is the analog of the congruence condition we had earlier. And fixing the degree of pi is analogous to fixing or bounding the size of p, which we were doing before. And so just as in the classical setting, if we can improve our non-vanishing result, then we get information about counting primes in progressions. Does this one go really high? No. So let me So everything we've done up to this point is actually pretty similar in terms of what's known in the integer setting and the polynomial setting. So the fact that we have this polynomial function instead of a holomorphic function is more convenient, but it turns out that complex analysts know how to do for holomorphic functions analogues of quite a lot of things that we know how to do for polynomials. So the difference between a polynomial in q to the minus s and a general holomorphic function is not actually that significant in practice. But one thing is different, which has to do with this non-vanishing, because while we can prove non-vanishing theorems for this LS chi by the same arguments that have been used in the integer setting, we don't need to, because we have this theorem of Weil, which is the analog of the Riemann hypothesis. LS chi is not 0 for real part of S greater than 1/2. And the proof of this is not purely analytic. The proof uses geometry. And then, I mean, you can tell a theorem is a really good theorem when it's proven multiple times. This theorem was proven 4 times. They gave 2 different proofs. One using the Jacobian of algebraic curves. One using intersection of curves in algebraic surfaces. And then Deligne gave a proof independent of Weil's using a lot of geometry. And then Stepanov and Bombieri gave a proof using the least amount of geometry, using only the Riemann-Roch formula for line bundles on algebraic curves. But there doesn't seem to be any way to prove this without geometry. I mean, I guess if you could perhaps prove it over integers as well. So this means a lot of problems that are hard over the integers are solvable in the setting of polynomials just using the Riemann hypothesis. So I guess for example, it gives us some good information on primes and regressions. It tells us the set of pi and fq join T monic, pi irreducible, pi congruent to A mod G, degree pi is equal to n, is equal to q to the n over phi of g times n plus O of degree g times q to the n over 2. So we have an error term of the same square root size. So the main term, the dominant, is q to the n. The error term is q to the n over 2. And it has dependence of the error term on the degree of g, but the dependence is of a very, very mild nature. But just as in the integer setting, the Riemann hypothesis does not come near to exhausting the questions you could ask about this L function. In particular, it doesn't answer any statistical questions. So the theorem kind of statistical questions about LS chi. So To go beyond that, to answer kind of the physical questions, you need to introduce further tools. And some progress on this was made by Katz and Sarnak, building on work of Deline. And in this case, there was further work of Katz that was needed. So I'll just say Katz, Sarnak. Kind of answer statistical questions. In the limit as q goes to infinity. And so what do I mean by that? So for a given chi, okay, actually, sorry. Let me say, let me introduce some new definitions. We'll say that chi is primitive if there does not exist chi prime of modulus g prime, where like g prime has smaller degree than g, where chi of f is equal to chi prime of f for all f relatively prime to g. So these are some characters of high modulus, high degree modulus, look very similar to characters of lower modulus. And these ones we often kind of ignore. And we'll say chi is odd if chi restricted to only well, I'll write it like this. Chi of g plus alpha is not 1 for some alpha in f cubed times. So if we restrict our character to the mod g to only the units of fq, only the elements of the finite field fq modulo g, we want the character to be non-trivial. And we call it odd because we think of these units as the analog of plus or minus 1 on integers. And Dirichlet characters that are non-trivial and plus or minus 1 are called odd. Another part of Weil's theorem is that if chi is primitive and odd, then LS chi is a polynomial in q to the minus s of degree exactly degree g minus 1. And all roots are exactly on the line on line 1 half plus it. And that implies that LS chi can be expressed in terms of the characteristic polynomial of a unitary matrix. Because forcing LS chi to have the roots on the line 1 half plus it means this polynomial has roots on the image of the line 1 half plus it under the map q to the minus s, which is a circle. And polynomials with all roots on a circle come from matrices with all eigenvalues on the circle, which are unitary matrices. So LS chi is equal to the determinant of 1 minus q to the 1 half minus s theta for some theta in unitary group, degree g minus 1. And what they said is that if you take any continuous function of this polynomial, so any continuous conjugacy invariant function of the group, if you average that over all chi's, and you average that over all unitary matrices, you'll get the same answer in the limit as q goes to infinity. Let me write that down on a different slide. So that was T2. Yes?
You assume that the t is greater than 0, but do you know the analog of Chalmers' conjecture? There's no vanishing at 1/2.
So there exists, no, I mean not directly, no. So there exists, to study that question in the polynomial setting, you would either have to use the same methods people use to study it over the integers, or a new method. And there do exist new methods in the setting that don't exist over integers, but they're not strong enough to apply to all Dirichlet characters. I mean, in fact, the statement is not quite true. So one can construct examples of Dirichlet characters which really do have L1/2 chi is equal to 0. You can't construct many, but this was done by Wanlin Lee, and she gave counts of how many you could construct.
When you view this identically, you also have the prime at infinity. So
Yeah.
what is the condition that the character is ramified, that they're the same as?
Yeah, so odd is the same as ramified at infinity, yes.
Okay, in other words, it's better to correct it by some factor.
Exactly. So if your character fails to be primitive or fails to be odd, you have to put some correction terms, and I just don't want to talk about the correction terms, so I'm just going to restrict to primitive odd characters. So what they did, so in this case it's due to cats, if you have, well, I'll say degree g is m, and then g square free. So no repeated roots. If you have some function, let me call that theta chi, function from u m minus 1 to c, which is continuous and conjugacy invariant. If you sum that over all chi that are primitive and odd, modulo g, sum f of theta chi, and divide by, well, you can just do q to the m here if you feel like it. Take the limit as q goes to infinity. This will equal the integral over u m minus 1 times f of theta. So this is the form of all the kind of statistical questions we want. They can all be expressed as trying to understand the average of some function over these theta chi, because theta chi determines the L function. Any question you have about the L function, you can express in terms of theta chi. And so you average, and you know what the average is, not exactly, but in the limit as q goes to infinity. And it's equal to some average over unitary matrices. Here I'm integrating against Haar measure. Maybe we'll put that. Integrating against our measure. And part of the reason that I'm bringing up this theorem is, in addition to answering a lot of statistical questions, it tells us why statistical questions are the kind of the main questions that we have to consider here. Because there kind of aren't any more non-statistical theorems to prove. I mean, this is a slight exaggeration. But if you were trying to prove a theorem that was true, not just on average, but true for every single L function, beyond this, beyond saying it has to come from a characteristic polynomial of a unitary matrix, then what your theorem would do is it would restrict this polynomial to only coming from certain unitary matrices. You would lie in a subset of this unitary group UM-1. But it's very hard to find such a theorem because this theorem tells you on average for large Q, you're everywhere in this group UM-1. It's every subset with non-empty interior will contain something with large enough Q because of this equidistribution result. So,
but if you count the number of characters, since you take only primitive ones, the number is not Q to the...
It's close enough. So in the limit, yes, it is. You're correct. It is not that, but it's in the limit as Q goes to infinity. It's the same thing. But there's something very unsatisfying that limit as Q goes to infinity, because, well, we probably don't care in the real world about the limit as Q goes to infinity. We care about maybe a particular value of Q. In particular, because there's no analog of this limit of Q goes to infinity in the integer analogy. You can't take the integers and set some mysterious parameter Q to infinity. It doesn't make sense. So a better analog of the statistical questions over the integers would be statistical questions for polynomials with fixed Q, but this parameter m the degree of g is going to infinity. And these kinds of statistical questions, the theorem of Katz using the idea of Katz-Sarnak and the theorem using the method of Deligne, can't answer for you. It can't answer questions in the degree m limit. And these questions are much harder, but they are not completely unsolvable. So let me state next, the first original theorem of this talk, I guess, which I need to some fiddly things. So, which is going to be about this moment problem that we mentioned earlier in the large M limits setting. So we let FQ be a finite field. And G in FQ join T plus a square-free polynomial, so a polynomial with no repeated roots. Of degree m. I'm going to sum over chi from FQ join T mod G, chi modulo G, which are primitive and odd, L 1/2 chi. So I'll choose this point 1/2, this central point, as being the most interesting one, raised to the power k. And here I am going to divide by the actual number of characters, which is q minus 1 over q to the m minus 1 times q minus 2. equals 1 plus O of k to the m, the mk minus k minus m, q to the 1 half. Q to the 1 minus m over 2. And this constant here is totally absolute. It doesn't depend on q, on m, or even on k. And I could probably tell you what it is. It's like 5 or something. It's not very large. So what is this saying? This is considering a moment problem, an average of a power of L1 half chi, but not the most common type of moment problem. Most commonly, people will consider moments powers of the absolute value of L1 half chi, so raising it multiplied by its complex conjugate to equal powers. Here, I'm taking powers without the absolute value, so the complex conjugate doesn't appear, which is a little bit less often considered, but is a kind of moment problem. I'm summing it over all the primitive odd characters, and I've divided by the number of primitive odd characters. And I'm telling you what the average value is. The main term is 1. So the typical average value is 1. And then the next thing is the error term. We're going to be bounded by a constant times this. And so I want my error term to be less than 1. So the key thing is we're letting m grow. We were interested in the case where m grows in q fixed. And so all our terms, you'll notice, are most exponential in m. So these terms are growing in m, and this term is shrinking in m. And so we want this term to win, so that the error term is smaller. And then this is like, so this is useful if q is greater than k squared times 2 to the 2 k minus 1. Because in that case, this term will shrink exponentially in m faster than these terms grow. But even for fixed m and letting q goes to infinity, even the setting of Katz-Sarnak, this is a more powerful estimate than you can get from their theory, because they get the limit as q goes to infinity, or more precisely, they show convergence with an error term of size 1 over square root of q. So q to the minus 1 half. Whereas here, I'm showing convergence with error term of power of q potentially much greater than q to the minus 1 half. So in number theory, there's a lot of different estimates for moments for different families of Dirichlet characters, and also beyond Dirichlet characters for other kinds of L functions. What's kind of special about this compared to all those other estimates is, or almost all of them, this power can grow arbitrarily large. So typically in number theory, you'd prove it for the first moment, or the second moment, or the third moment, or the fourth moment, maybe up to the 8th moment. But for q sufficiently large, I can prove this for like the 2000th moment or something like that. I can prove it for any moment I want. And so that is the power that's available in this finite field setting that is not really viable over the integers. But that's not the main thing I want to talk about. The main thing I want to talk about is, where does this estimate come from, and why does it involve geometry? So why is geometry something you need to consider when you're thinking about these moment problems? So this question has a geometric nature because it can be expressed in terms of counting solutions to equations over finite fields. Polynomial equations specifically. Solutions to over FQ. Solutions maybe in FQ. So what we have is some problem involving the arithmetic of this ring of polynomials in one variable over FQ. And so what we want to do is re-express it in terms of only the base finite field FQ by taking the polynomials and just looking at their coefficients one at a time. And we'll end up counting solutions. Now we have many more variables, a system of many equations in many variables over the finite field FQ. I mean, it's not obvious from the theorem where any equations are appearing, but in fact, I'll show where equations show up. And then the solutions to polynomial equations over a finite field are something we've known since the middle of the 20th century, can be interpreted as a geometric object, very closely connected to the solutions of a similar system of equations over the complex numbers. And so the kind of techniques you need to count solutions to equations are the same kind of techniques that you would need to study the topology of the solutions over the complex numbers to the same equations. What I'll do next is I'll explain how polynomial equations arise in this setting, and then I will explain how the counting works. So the idea is you take the sum on the left side and you expand out using the definition of LF chi, L1 half chi. So you end up with left-hand side is equal to q minus 1 over, or the q minus 1, q n minus 1, q minus 2. Times the sum over chi. And so each L1 half chi becomes a sum over f. So we end up with k sums over f. Sum of f1 through fk in fq join t plus. By multiplicative chi, the chi term just becomes chi of f1 through chi of fk. And then we have q to the minus s times degree f1 up to s times degree fk. So I'll write this as degree f1 plus degree fk times s. And so in number theory, whenever you've got a double sum like this, you want to think about what happens when you switch the order of the two sums. So you have a sum over chi of the evaluation of chi at this product, f1 through fk. And that sum we can evaluate using orthogonality of characters. So q minus 1 over q to the m minus 1, q minus 2, sum over chi, odd, primitive, chi of, let's say chi of h, this is equal to 1 if h is congruent to 1 mod g. If h is congruent to 1 mod g, all the characters have value 1, so their average is 1. It's equal to minus 1 over q minus 2 if h is congruent to alpha mod g for some alpha in fq times not equal to 1, and is 0 otherwise. So if we're averaging...
But since you take only primitive characters, the number is not quite what you have written.
Oh, it's OK.
So you have to correct it by the suitable C to get exactly 1 on the right-hand side.
It is OK. Sorry, I forgot this. So because my g is irreducible, every odd character is primitive. Because the only non-primitive... I did this for simplicity. It's not a restriction of the actual theorem in my paper. But just for this talk, g is irreducible. And so because g is irreducible, all the odd characters are primitive. There's only one non-primitive character. It's the trivial character, which is also not odd. So I'm only counting the odd characters. And this is, I think, the correct formula for the number of odd characters. And so if I were summing over all characters, you just get 1 if h is congruent to 1 mod g and 0 otherwise. So the sum over odd characters, the sum over all characters, minus the sum over even characters. And so this negative term comes from the summing over the even characters. Or minus 1 over, over q minus 2. So if you plug that in, what you get is simply the sum over f1 through fk in fqt plus. Let me write it like this. Sum over alpha in fq cross. f1 through fk, where the product is congruent to alpha mod g of w of alpha, where w of alpha is just given by this formula. W of alpha is equal to 1 if alpha is equal to 1, and minus 1 over q minus 2 otherwise. Is equal to w of alpha times q to the minus degree f1 plus dot 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 plus degree fk, whole thing times s. And so another way to write that is the sum alpha in fq, w of alpha, times the sum from n equals 0 to infinity of q to the minus ns. So each term where this degree sums to n gives us q to the minus s. And the number of terms is the number of tuples f1 through fk and f cubed join t plus, whose product is congruent to alpha mod g, and whose degrees sum to n. So the original problem of moments of L functions, if you expand it out and use this identity, it becomes a counting problem. For each element of fq and each non-negative integer, we've got to count tuples of polynomials, monic, whose product is congruent to alpha mod g, and whose degrees sum to n. So what is this set? That we're trying to count elements of. Product F1 up to Fk. Well, let me write it like this. The product from I equals 1 to k Fi is congruent to alpha mod g. The sum from I equals 1 to k degree Fi is equal to n. What is the set we're trying to count elements of? So another way to express it, we can break it up into the union over tuples d1 through dk of non-negative integers that sum to n of the set of f1 through fk in fq join t plus, with degree of Fi is equal to di, and the same congruence condition. And this is the set of solutions to m equations in n equals sum I equals 1 to k di variables over fq. Why is this? Well, each monic polynomial of degree di has di plus 1 coefficients, which are in fq. But we fixed the first one to be 1, so we have di coefficients that vary. Those are our variables. So the coefficients are the variables. And so the coefficients of the product to k Fi are polynomials in those variables. And that's property is preserved when we reduce mod g. So we reduce mod g by polynomial long division, which gives us the polynomial of degree strictly less than m, which has m coefficients, some of them possibly 0. And each coefficient is a polynomial in the original coefficients. And we're setting those m coefficients to particular values, m minus 1 of them to 0, and 1 to a non-zero value. So we have m polynomial equations in n variables. And we're taking the union of this set over many tuples d1 through dk. Another way of saying this is the fq points of an algebraic variety. Although, because it's not obvious that it's irreducible, I should probably say scheme instead. So the tool that we will use to count these solutions is a general tool for counting solutions of polynomial equations over fq, or fq points of an algebraic variety. That was worked out by Grothendieck School. I think it's written on one of the windows out there, but the window I found it on, it was cut off, so I can't be sure it's this exact formula. But I think it is. So the theorem. Yes.
Say you apply the Euclidean algorithm and you get n equations.
Yeah.
But why would these equations be algebraic? Like is the Euclidean, because the Euclidean algorithm just does some weird things somehow.
So you don't need the full Euclidean algorithm. You're only using long division, which is one step of the Euclidean algorithm. And so how does long division work? We want to take the leading coefficient of the polynomial that we're modding out, and we want to cancel it using the leading coefficient of the polynomial we're modding out by, which is 1. So you just take the polynomial we're modding out by, multiply by the leading coefficient, shift it by a power of t, and then subtract. Those are all polynomial operations. Now you have a new leading coefficient. You multiply, shift, and subtract, and you just keep doing that. Every operation is arithmetic, so at the end you get something polynomial. Yeah, so for the actual Euclidean algorithm, there's something else we have to do, which is sometimes we have to check whether we get 0 or not, and then divide things. So you get I mean, it's not fully polynomial. You get rational functions in the Euclidean algorithm, but for just long division, you get polynomials. So the Grothendieck-Lefschetz formula is if x, okay. So, well, if x is a scheme of finite type over FQ, which I guess for simplicity you can also say x is a solution set of finitely many polynomial equations and finitely many variables over FQ, then the size of the set of FQ points of x, the number of solutions to the equations, is equal to a sum from I equals 0 to twice the dimension of x, minus 1 to the I, trace of Frobenius on the compactly supported cohomology of x with coefficients in the L-adic numbers. So there are some things that are unfortunate about this. Maybe the only thing that's unfortunate about this statement is that it's hard to explain clearly what Ital cohomology is if you don't already know what it is. But I will. So it's more helpful to say that it's very closely analogous to singular cohomology or de Rham cohomology or any of the cohomology theories we use for manifolds and therefore for algebraic varieties over the complex numbers.
You have to extend x to FQ.
Oh, yes. It's a very good point. But because it's defined in the arithmetic setting, it has this arithmetic feature to it. If we extend x to the algebraic closure over the finite field, which is analogous to how the usual cohomology theory behaves well when we extend our varieties to the complex numbers, which is an algebraically closed field, the Ital cohomology inherits an action of the Galois group of that field, acting by automorphisms of the variety and therefore acting by automorphisms of the cohomology. And the generator of this automorphism group is Frobenius, the automorphism that sends x to the q, or maybe to x to the 1 over q, I can never remember. And we want to take, so this is acting as a linear automorphism of cohomology. We take the trace, and we sum this in an alternating sum over the degrees. Since this cohomology group is defined over the field of L-adic numbers, this is a priori only an L-adic number. But the theorem is that in fact it's an integer, and it's equal to the number of FQ points.
Question.
Yeah, yes.
So, this probably doesn't work, and this is not explained, but when I see this big set, which I want to declare here, what I wanted to do, my first instinct, was to regroup based on the product of the Fi. So I just have the union over the polynomial congruent to alpha moduli Q, and then it's just kind of the number of divisors of, well, it's the number for it to decompose it into k factors. And this is just based on, this just depends on the decomposition in irreducible factor of my product. And so I was thinking, can't we somehow use the right term to be able to calculate this? I guess not if we...
Yes, okay, so that is a good question. So it is, you're completely right. So we can transform this sum into a sum over polynomials in a congruence class of this divisor counting function, which depends only on the factorization into irreducibles. And you can try, and so you can put this into a broader context. There's many other functions depending only on the factorization into irreducibles that I can write down, other than this divisor counting function. And you can try to sum those all in progressions. And one approach to summing these functions is to use Weil's theorem, use the Riemann hypothesis to count irreducibles in progressions, and to combine that information together to count polynomials which have factorization into a certain number of irreducible factors in progressions. And this gives you some estimates. And for some problems, it gives you pretty good estimates. So this is what we're, if you try to go back and then figure something out about L functions by this, you won't get any more information about the L function than you started with. So the kind of bound you'll get for the original moment is the same bound you would get by saying, what's the best bound on the individual L function I can get from Weil's theorem, which will be a little bit bigger than 1, the value at 1/2. The bound will be sub-exponential in M, but bigger than 1. And then averaging that over all the characters. So it's just an upper bound of size greater than 1. We're trying to prove something stronger. We're trying to prove an asymptotic of size exactly equal to 1 plus a small error term. So you do get something by that, but it's not as strong as we need. But this does suggest the right generalization. The actual theorem in my paper, which I'll talk about if I have time, is really a theorem about counting polynomials in progressions with certain types of factorizations. Bring 2 up, 3 down.
Question before you erased your error. I have been wondering what you meant by the big O. You sort of said it, but I'm a little bit unsure. You have 3 integer variables.
Yeah.
K, M, and Q. And it sounds like you mean the big O in the universal non-asymptotic sense that for all that there's a constant bound across all possible values of all 3 integer variables.
Yeah.
Okay.
Yes.
So that's just the strongest sense in which you could have meant the big O.
Yeah. And then in and the methods that I have, it gives you a very, very precise bound. So for a lot of problems, it's actually very natural to state a bound using this method without any constant factor, just an explicit bound on the error term. I just put the big O because that lets you simplify the expression kind of. So, but it's because of the nature of the method using the growth and Lefschetz fixed point formula, it gives very concrete answers kind of, and very, if you do it correctly, very, very uniform answers. So the other theorem that we need very crucially is Delign's Riemann hypothesis, which states the eigenvalues of prob Q acting on HIC of X FQ bar QL. So this is a vector based over the analytic numbers. A priori, these eigenvalues are analytic numbers, but in fact, they're algebraic integers. They're solutions of polynomial equations over the integers, which means that you can embed them into also the complex numbers. Look at the solution of the same equation over the complex numbers and then take their absolute value. And it's bounded by q to the I over 2. So what's the corollary of that? The trace of Frobenius on the ith compactly supported cohomology group of X FQ bar QL is bounded by q to the I over 2 times the dimension of this cohomology group. Just by the very obvious theorem in linear algebra, the trace of a matrix is bounded by the largest eigenvalue times the dimension. And so what you have to do to solve these counting problems of solutions of polynomial equations over FQ field is to first compute as well as possible these cohomology groups. In particular, you would very much like to calculate the cohomology groups in high degrees for I large, because these give the largest contribution in Delign's theorem. Calculate as many of them as you can, and for the ones you can't calculate exactly, you need to bound the dimension. And then you apply these theorems. For the ones you can calculate, you calculate the trace exactly, and you see what it gives. And for the ones you bound the dimension, you get a bound from Delign for the error in your estimate which those cohomology groups introduce. So in this particular case, you get the following answer, the number of solutions to the counting problem. I have to pull it up. Is first the main term plus O of k to the m k minus m sorry, let me actually write it in more detail, slightly smaller. K to the m minus 1, mk minus k minus m plus 1, m plus 1 minus m, q to the 1/2, plus k to the m minus m plus k minus 1, choose m, mk minus m minus k, choose n minus m, q to the m minus m over 2. So this is a messy formula. Let me say something about what it means. So the first term is the expected answer. And it's what you get when you average the count over all residue classes relatively prime to G. So you might expect to get similar answers for different alpha modulo G. And if you sum over all residue classes, you can calculate the answer explicitly, the count explicitly, and it's given by this exclusion. And then you divide by the number of residue classes, which is q to the n-1. And this is the expected answer. And everything else is an error, and it's in with it's inside of a big O. So the rough form of the main term is q to the n minus m. There's m equations and n variables, so it's like we roughly have n minus m free variables. The expected form is q to the n minus m. And then the important thing about the error term is that there's this q to the n minus m over 2 here. So the error term is of the square root size of the main term. It is what we would get if it was totally random, times these funky factors with binomial coefficients. And these are going to be growing exponentially in m. But if q is large, they're growing exponentially in m slower than q to the n minus m over 2. There will be a lesser contribution. And if you sum this over all values of n, and you simplify it slightly, you get the L function estimate that I claimed earlier, which I think is, yes, which is now erased. So this counting estimate implies, by a simple calculation, the L function estimate. And everything comes down to this counting problem, which comes down to geometry. It comes to calculating these cohomology groups.
What are the DIs?
So this is taking the union over all the DIs, because my formulas simplify when I sum over all the DIs summing to n. I could give you formulas for particular DIs, but they would be messier. But yeah, this is for the union.
And alpha is not 0. Alpha.
Yeah. So this is valid for, in fact, for any residue class mod G other than 0. Yeah. So not just for alpha and FQ. But yeah, this is for alpha non-zero and FQ. So then what is the key geometric statement? So the geometric statement makes sense over any field. So G monic square free degree m over a field. Let's call it F. A and f of t modulo G with no common factors with G. And we're going to look now at the union of d1 through dk in positive non-negative integers whose sum is n of now the variety parameterizing tuples of polynomials f1 through fk whose product is congruent to A modulo G. Degree Fi is equal to Di monic. Okay, maybe I should say scheme because it's not obvious it's irreducible. So one way to say this is a scheme whose points over any ring are tuples of such polynomials over that ring, or in particular, so in particular over the complex numbers, the complex number valued points would be solutions to this equation. Polynomials over the complex numbers satisfying this congruence. The union of the scheme, I'll call that X. Let me make the dependence on A explicit. Then the cohomology of X over the algebraically closed field with coefficients in QL splits into a kind of a boring piece, which is XA, which is independent of A, plus like an interesting piece. But the interesting piece is zero-dimensional if I is not equal to n minus m or n plus 1 minus m. And its dimension is given by this formula, or its dimension is less than or equal to k to the m minus 1, mk minus k minus m plus 1, choose m minus m plus 1 if I is equal to n plus 1 minus m, and it's less than or equal to k to the m minus m plus k minus 1. Choose m minus 1 times mk minus m minus k. Choose m minus m if I is equal to n minus m. Yes, it vanishes. So the interesting piece vanishes. So this theorem, I mean, so the precise version of the theorem involves telling you what the boring part.
Why you didn't put q to the I over 2 in your stuff there up there?
Well, there's a q to the n minus m over 2, and there's a q to the 1 over 2 up there. And so by combining those, like the interesting values of I are q to the n minus m and q to the n plus 1 minus m. Yes. And those are the values that appear here because of this q to the n minus m over 2 factor and the q to the 1 over 2 factor.
No, but why the q1 over 2 is not qn minus m? Oh,
the whole, sorry, I got a little compressed. The q to the 1 over 2 is being multiplied by n minus m over 2 because of the way the parentheses. Yes. Yes, sorry about that. There's an extra set of parentheses over there that's multiplying it. So this theorem, it implies the counting. When we take this over a finite field, it implies this counting statement. Once you calculate what the boring contribution gives and relate it to the first term, the interesting contribution gives the second term. But you can also take it in this complex number setting, and it's a topological statement about the complex, those complex space parameterizing tuples of polynomials. This is not necessarily a complex space you would consider if you didn't have this number theoretic problem, but is a perfectly reasonable complex space. And the kind of methods that you need to apply to answer this question in the finite field setting are also the kind of questions, the kind of methods you need to apply to answer the topological problem over the complex numbers. Yeah, let me just say a few words about how this goes, and then I'll stop for questions. So the key thing which makes it nice to study this family of varieties is that they live. So is this A parameter, the fact that they change nicely when you vary A. So A lives in this set of polynomials modulo G, which are relatively prime to G, which if you think about it, geometrically corresponds to a torus. There's a torus parameterizing the valid values of A. And as you move A in this torus, the XA space changes shape. And the key method we use to study the topology is the method of comparing how much the topology changes, how does the cohomology change as we move from one value of A to the next. So it's possible to get good control in the cohomology for a generic A, a random A, and then one can show it's not too different for a specific value of A, using this theory of vanishing cycles, which says the cohomology only changes when the space develops singularities. And you can check, it's a totally elementary calculation, that this space has very few singularities. In fact, has a zero-dimensional space of singularities for every given A. And so the fact that the singularities are so small turns out to be what's crucial in proving this theorem. Yeah, OK, I think now is a good time to stop.
So here the cohomology is not exactly a local system on the torus, I understand, but you can control the vanishing cycles?
Correct. So this cohomology, it comes from a constant complex on the torus, a complex of constant sheaves. And this cohomology, it comes from a perverse sheaf, and then or a shift of a perverse sheaf. And then, yeah, I just do vanishing cycles on curves in the torus. And that's how you can show the perverse sheaf has cohomology that is not vanishing only in 2 degrees. And then you need separate methods to control the Betty numbers of this perverse sheaf once you control the vanishing.
Yeah, so I have a question. So can also so do you compute the cohomology by comparing it with the cohomology of the complex object, or can you do it for each characteristic?
No, the method is in each characteristic. So the tools you would need if you wanted to compare it to what you get over the complex numbers, you would need to control how this cohomology changes as you vary the base field from C to P, and you would use the same exact set of tools of vanishing cycles. So you would need the same analysis of the singularities, also the same compactification to do this comparison. And so basically because of that, it seems to me to be more efficient to work directly in each characteristic rather than doing the comparison. But for some results like this one, it absolutely is true that you need to go to the complex numbers to use some tool that's only available there.
Yeah, may I come back to the Katz theorem? Yeah. Interpretation you gave. The theorem about unitary matrices that equidistribute over the unitary group as Q tends to infinity.
Yeah.
So, you mean that this theorem kills hope to for the kind of estimates or whether theorems like in the Dirichlet style or not?
No, okay, so it only kills hope for theorems of a particular type. So one is that we need to keep the L function out of some open subset in the space of unitary matrices, and the other is the open subset should be independent of Q. If I have a theorem that is about keeping out of, say, maybe a closed subset, like for example this Charlotte conjecture trying to show it can't be 0, then that is not ruled out by Katz's theorem. And if I have a theorem keeping out of an open subset which is depending on Q, then that's not also ruled out. And in fact, such statements exist. So the trace of this matrix is because it comes from only the degree 1 polynomials, you can see the trace always has to be at most root Q. So if m, the degree of G, is larger than Q squared plus 1, the fact that the trace is bounded by root, no, sorry, it's greater than root Q plus 1, the fact that the trace is bounded by root Q is a non-trivial restriction. It's avoiding some open subset. But that's OK because that restriction goes away as Q grows. And so there do exist non-trivial restrictions that go away as Q grows that hold for every single L function. My just experience is that the ones that are useful follow from, on the one hand, Weis-Riemann hypothesis, and on the other hand, the bounds for the first few coefficients that come from the Euler product formula. So most, I'm not sure exactly what estimates you're referring to, but most estimates on the L function you would want in analytic number theory that are not statistical are for a particular one. They follow from kind of those two results. And so that's why the statistical ones seem to be more interesting in this case. Yeah?
So for your theorem, you have an estimate on s equals 1/2. If you use the functional equation, is it trivial to derive an estimate for real part of s arbitrarily close to 0 in the same way?
Yes. So the theorem, in fact, it applies equally well to everything in the right half plane. Everything real part of s greater than equal to 1/2. There's an analogous statement. And then using the functional equation, you would get the analogous statement for real part of s. Oh no, there's something slightly subtle, which is because I didn't put the absolute value in, the constant of the functional equation matters. So the Gauss sum matters. So you can't just take this and flip it around and get an estimate on the other side for real part of s less than 1/2. That would be a different theorem. However, for real part of s, I think it would be easier if real part of s is close to 0, then using the traditional method, using the fact that you apply the functional equation, the real part of s is close to 1, the sum is now a sum of a function that's decaying very rapidly, then the kind of more traditional analytic methods, I think, should be able to handle that one OK.
One, yeah, so close to 0, and when you use the functional equation, you have the Gauss sum, so, I mean.
Yeah, I don't know. OK, yeah, maybe not. Yeah, maybe that's something interesting. Yeah. So for close to 0, this theorem doesn't directly help. And or does it? It gives you something. I need to think about it. I need to think about it.
The second question is more naive. Can you derive some analog for Eisenstein series on GLN by the same sort of technique?
Probably not by the same technique. I definitely think understanding moments of L, like you mean like moments of L functions of higher rank automorphic forms or something? Yeah, so I think for moment L functions of higher rank automorphic forms, by trying to get that by geometric methods is a very interesting idea. The geometry you get by doing that would certainly be something very different. So you wouldn't get this kind of simple congruence condition. You get something complicated involving, vector bundles or something, involving these adelic double quotient spaces. And the geometric methods that are needed might be more complex, but I definitely, it's definitely possible, but it would require completely new geometric ideas.
Okay, so